Hey everybody, this is Larry. This is me going with Q3 of the bi-weekly contest 128. Minimum time to visit disappearing nodes. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So this one, to be honest, I did this in about 5 minutes. I probably should have and could have done it faster. Especially, if I wanted to move up in the leaderboards. Though actually people, I guess, did okay on it. But my biggest thing was just that I'm trying to be careful on this one, but and want to make sure that I don't miss any edge cases, right? Because every edge case costs 5 minutes or so. But let's say we don't have this disappearing trick. If we don't have the disappearing trick, then it is just Dijkstra, right? Dijkstra. Because this is shortest path, or pairs shortest, or not all pairs, but single source. What's it called? Single source shortest path to all nodes. That's fine. It's not precise enough, but you get the idea, right? But we do add a little bit of a wrinkle of this disappear, and there are some edge cases about this disappear which we'll talk to, but otherwise it's just Dijkstra, right? And let me just type it out so that you can kind of, Google for it if you need to. I'm not going to go over Dijkstra's algorithm in this video. It is, I wouldn't say it's basic, but it is just definitely something that is fundamental. You need it for your interviews, you need it for your competitive programming, and also there's a lot of random things with it that I'm not going to get into, right? So I'm not going to go over Dijkstra, but I am going to go over the difference, right? Now the difference is that a node can disappear at a certain time. And you ask yourself, how does that affect things, right? And it turns out not that much, because Dijkstra algorithm by its construct and by its proof is a greedy algorithm, right? Basically, the Dijkstra's algorithm in English maybe a little bit sloppy, it's not quite the implementation in algorithm, but is that you're trying to get to every node as early as you can, and that sets you up from getting from that node to every other node that you haven't seen before in the shortest way that you can, and so forth, right? So basically this idea of taking min paths from different places, taking different stops. So what that means with this disappearance is that if you already get there as early as possible in the shortest path kind of way, and it disappears, that means that you couldn't have gotten there any faster, right? There's no choice because by the construct of the Dijkstra's algorithm, there are no choices that allows you to, it's not like you have to make a decision to go to here first, because by the definition of shortest path, the shortest path of you getting there is already the shortest path. Maybe you could say that by some contradiction or something like this. I don't know, right? So that means that if you can't get there before it disappears, you just can't get there. So that's basically the only difference. And you could have done it. And I think the only nuance about this one is that I thought about two ways of doing this. One is just run the regular Dijkstra's and then do a for loop afterwards, right? But you have to to filter out the things that we cannot reach. But that's not quite correct, because then now you may say that you're going from that disappeared node to another place, maybe, if you just run the normal Dijkstra. So you have to be careful and change the way that you pick edges that you can go next, or nodes that you can go next. And that's basically what I did. Let's go over the code. We'll go in some detail, but yeah, this is just converting it from an edge list to an adjacency list. You see this a lot from me, but yeah, it just contains the node and the rate. And this is the heap part of it. Heap and storing the best, the shortest path from 0 to the ith node. So we start off with rate, the distance of 0 and the node of 0. We set it to 0, right? And this is just regular heap pop. This is so that we don't relax the same node twice without improvements. And here is just regular, well, most of this, right? Now we go for every edge to see which node we can relax. This part makes sense. So far, still Dijkstra, still in preparation, as some people may say. It is just Yeah, if adding this edge gives us an improvement, then we'll consider it. But this is the only thing that's different than regular Dijkstra, which is that we have to get there before it disappears, right? That's it. That's the only difference between this and Dijkstra, and maybe like -1 or something, right? Whatever. But yeah. And yeah, if you do, then we add that node to be relaxed, and that's pretty much it. And then at the end, if we're not able to go to it, meaning that it is infinity, we just set -1, and that's it. Yeah. What's the complexity here? Well, this is Dijkstra's. Each node should get relaxed once. So yeah, it's gonna be v times y. No, not quite. What is it? Well, v log y. No, y log v. Sorry, I mixed them up. But yeah, it's gonna be y log v. This is pretty standard stuff. You can we actually reduce this to v log y, but we're not gonna get into the hows and the whys. Wait, is that true? No. This is y log y, maybe. I don't know. Man, I'm just having a rough day. But yeah, y log y, which is roughly y log v anyway. So different implementation, but this way is y log y. And yeah, and that's pretty much it. This is, like I said, this is basically vanilla Dijkstra's algorithm with just this if statement, or this part of the if statement that I would consider be different. So yeah. So that's why I kind of was like 5 minutes. It's a little bit long for just writing Dijkstra, but I also was trying to be careful about edge cases. And like I said, there are a couple of edge cases, especially the one where you get there exactly the same time, which luckily is in the examples because I would have gotten it wrong. I mean, it's unclear. Yeah, it's unclear whether you can get there at exact, or like what happens to be exactly the same time. But I would have gotten it wrong because my interpretation is that you could leave it at the instant, but luckily that is on the cases. But yeah, that's all I have for this one. Let me know what you think, and you can watch me solve it live during the contest next. Yeah, so we're having issues again. A little bit slow on this one, to be honest, because I feel like I got the idea immediately, but I was just typing it slow. Or verifying it slowly. The node disappears, huh? When does it disappear exactly? What if you're there? Oh, what's output again? Oh, each node. Okay, so just by no, with Dijkstra's, right? How people not done with this already? Yeah, people are done with this already. Okay. Node 0. Is that enough? Is that too many hedges? Don't know. No, it should be okay. Okay. It's not DP or anything weird. Okay. Let's see. up. Do I want? Does it ever make sense for multiple? No, it doesn't, but it shouldn't matter. Okay, fine. If this is less than plus of p. Takes two. I always forget. Yeah. Oof. Oh, it disappears exactly. Okay, so it has to be this. That's what I was checking for, but I wasn't sure. That would have been a very silly mistake. Because it's an example. If it wasn't an example, it would have been fine, but... Alright. Thanks for watching, everybody. Thanks for the support. Yay! Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this forum, explanation, description, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.